Hello, good afternoon, and today in this video we are going to see the proof of Euler's theorem. Okay, so if we talk about Euler's theorem, okay, it is nothing but it is a equation which gives us this: e to the power I theta is equal to cos theta plus I sin theta. Okay, and we are today in this video we are going to see the proof of this very equation. Okay, in order to prove this very equation we take the help of the Mac Laurance series. Okay, so if you are not well aware of a Mac Laurance series, then let me introduce a series named as Mac Laurance. So if any function f of x is given, you can expand it in a way such that f of x is equal to f of 0 plus f dash 0 x divided by 1 factorial plus f double dash 0 times x squared divided by 2 factorial plus f triple dash 0 x cube divided by 3 factorial and so on. Okay, here f dash is the first derivative of the function f, and f double dash is the second derivative, and f triple dash is the third derivative and so on. Okay, so okay, and how this come into the picture, then in order to understand this you have to go through another proof, another function which is known as something called this: f of x is equal to f of a plus f dash a x minus a divided by 1 factorial plus f double dash sorry f dash a, and now yeah, it's f double dash a x minus a times whole square divided by 2 factorial and so on. This is called as Taylor series, and if you put a is equal to 0 over here, you get this Mac Laurance series. Okay, you can we can also use this Taylor theorem to solve problems in SHM too, and it can be used in various field of science. Okay, so I'm not going to go with the proof of this Taylor and Mac Laurance series. At this point, I'm assuming that you know the Mac Laurance and the Taylor series. Okay, the proof we will talk about the proof of these two series in some other video. So by using this Mac Laurance series, uh, we uh, we we find the expansion of e to the power x, because here on the left hand side we are here getting something called e to the power I theta. So using Mac Laurance series, we are gonna to derive the expansion of e to the power x, which is 1 plus x squared divided by 2 factorial plus x cube divided by 3 factorial and so on. Okay, now similarly for sin x, it is x minus x cube divided by 3 factorial plus x to the power 5 divided by 5 factorial minus x to the power 7 divided by 7 factorial and so on. And similarly for the cos x, it is 1 minus x square divided by 2 factorial plus x to the power 4 divided by 4 factorial and so on, with alternate plus minus. Okay, okay, how I can write this equation? Okay, so we defined f of x is equal to e to the power x. F dash x is nothing but e to the power x. F of 0 is nothing but e to the power 0, which is 1. So f of x is f of 0 plus f dash 0, okay, x divided by 1 factor and so on. So f of 0 is nothing but 1 plus f dash 0 is also 1, so x divided by 1 factorial, and if you continue this series you will get the next term and so on so on. Okay, so this is our free expansion by the Mac Laurance series. Now, in the very first expansion, the very first term, instead of e to the power x, instead of x, we put I theta. Okay, so what we got as e to the power I theta is equal to 1 plus I theta plus I theta whole square divided by 2 factorial plus I cube theta cube divided by 3 factorial plus I to the power 4 theta to the power 4 4 factorial plus I to the power 5 theta 5 divided by 5 factorial and so on. Okay. Now we will isolate the real part on the one side and the imaginary part on the other side. Okay, so we got 1 minus theta square divided by 2 factorial, because I square turns out to be minus 1. So this will give you minus theta square divided by 2 factorial plus theta to the power 4 divided by 4 factorial and so on, plus I times theta. Okay, and minus theta cube divided by 3 factorial plus theta to the power 5 divided by 5 factorial and so on. Okay, till infinity. Okay, and if you closely look, this is something 1 minus x square divided by 2 factorial plus x to the power 4 divided by 4 factorial, just like this. Okay, just like this. So if I replace in this very term x with theta, we got we got cos theta is equal to 1 minus theta square divided by 2 factorial plus theta to the power 4 divided by 4 factorial and so on, which is nothing but this. And here you can also relate this theta minus theta cube divided by 3 factorial plus so on. It sound like this is the expansion of sine x. Okay, instead of x, if we put theta, okay, so sine theta will look like something theta minus theta cube divided by 3 factorial plus theta to the power 5 divided by 5 factorial and so on till infinity. So e to the power I theta is nothing but cos theta plus I sine theta. So hence proved. Okay, so this is the algebraical way to prove the Euler theorems. So first of all, we take the help of the Mac Laurance series for the expansion of e to the power x sin x cos x. Why? Because it is there in our equation. Okay, then using Mac Laurance series, we find the expansion of e to the power x. Then we put I theta instead of x, because in our equation I theta is given. There is no x in our equation. So when we put I theta in our equation, we get this a new series where we separate the real part and imaginary part, and we find that real part is nothing but the expansion of the cos x, and the imaginary part is nothing but the expansion of sin x. Putting this to value, we get our desired result. Thank you. This is all about in this video. Thank you.